Hello, everybody. It's Mrs. Pound, and I am here with more about types of machines from chapter 4.3. And our machine for today are levers or levers, however you would like to pronounce that, from section 432. So our objectives today will to be to classify and compare different types of levers and to calculate mechanical advantage of a lever. So you use levers all the time. Maybe you can think of some examples of levers that you know about. A lever is a simple machine made of a rigid bar that pivots at a fixed point. And so here in the background, I have a hammer. And a hammer is actually two different kinds of levers. It's one kind of lever when you use it to pound in nails, and it's another kind of lever when you use the claw of the hammer to remove nails from a board. When we talk about levers, we talk about a fulcrum, and this is the point at which a lever pivots. So here in this picture where we have the seesaw is a lever and it pivots right here. This is the fulcrum. Now, in a first class lever, there are three different classes. There are three different classes of levers. So the first class of lever we talk about is a first class lever. And in this type of lever, the fulcrum is in the middle between the input force, the effort, and the output force or the resistance. Here, that output force resistance is also called the load, so it can have many different names. So go ahead and copy this diagram into your notes in the space that is provided. The input force and output force are in opposite directions. So if you put effort over here, the load or output force goes up. So go ahead, so I know that you're listening, and draw an up arrow here by the load to show that that goes up. Some examples of first class levers are scissors. If you look at the scissor here, there's the fulcrum right there in the middle, a crowbar, a seesaw, and the claw of a hammer. A crowbar and a claw of a hammer work very similarly, so they're pretty similar. They do the same thing. Now, a second class lever, the resistance force lies between the fulcrum and the effort force. So here we have the fulcrum at the end. We have the load or resistance force in the middle and the effort force at the end. And we notice if we lift up on this, the load also lifts up. So the input force and output force are in the same direction. So go ahead and put an arrow next to or on top of that load to show that you're listening and to show that the two forces are in the same direction. And just think of something. What do you do that with? What do you lift here and it lifts the load in the middle and the fulcrum is at the end? Perhaps you thought of a door, a bottle opener, a wheelbarrow, or a furniture dolly. I probably would have thought of the wheelbarrow here because on this wheelbarrow, the wheel would be the fulcrum, the resistance force is in the middle, and you are applying effort at the other end. Also, a door is an example because the hinges are the fulcrum, the resistance force is the door in the middle, and the handle at the other end is where you put your effort force. Now, think about this too. You really want that handle on the other end of the door as far away from the fulcrum, the hinges, as possible, because think about if it was placed in the middle or even really close to the hinges. That would make the door actually really hard to open. Now, in a third class lever, the effort force lies between the fulcrum and the resistance force. So here is our effort, here is our resistance. Now, when we use this type of lever, there's a gain of speed and distance with a loss of force. So when you do calculations for this, the mechanical advantage is actually a fraction. It is a number less than 1. because we want speed and distance, not force. Another thing to note is that the input force and output force are in the same direction. So go ahead and next to or on top of the load here of the picture that you've drawn, draw an up arrow to show that the effort and load are in the same direction. Now, can you think of any levers that work this way? Some examples are a hockey stick, tweezers, a baseball bat, a tennis racket, and a broom. So if we take a look at the bat here, and I know it's hard to see in the background there, but or even just think of a bat. So a lot of these things have to do with sports. We use a lot of third class levers in sports. We also use them when we're doing chores like a broom. And what your effort here is where you hold it. The fulcrum is actually the tip of the bat toward you, and your resistance force is here where you hit the ball with the bat. And so with this, you are not multiplying your force. You're actually giving that distance and speed. And if you were to calculate the mechanical advantage, and let's say you came out with a mechanical advantage of 1/2, you could figure out how much that increases your speed by just using the inverse of that fraction. So your mechanical advantage is 1/2, so it lowered your force, but your speed is doubled because that is the inverse of 2. Now, there is a special formula for finding the mechanical advantage of levers, and it is the length of the effort arm divided by the length of the resistance arm. And so we can see here, if we want to increase mechanical advantage, we want a much larger effort arm than we want a resistance arm. So that is one way to increase mechanical advantage of this. So let's try this formula out. And an example of a problem is, what is the mechanical advantage of a lever if the length of the effort arm is 2 meters and the length of the resistance arm is 1 meter? So we have our equation. We plug in our numbers. 2 meters divided by 1 meter, 2 divided by 1 is 2. Remember, our units of meter cancel out, so we are left with a number that has no units. Another example of a problem might be, how much force is gained from a lever with an input force of 30 newtons and an output force of 120 newtons? Remember, going back to the previous chapter, one formula we can use is mechanical advantage equals the output force divided by the input force. When we plug in our numbers, 120 divided by 30, we get 4 times more force. 120 divided by 30 is 4. The newtons cancel out. So 4 times more force was gained. So our objectives today were to classify and compare different types of levers. There are 3 different types, and to calculate mechanical advantage of a lever. So don't forget your 5 questions, and next time we will talk about pulleys.